Today we're going to be learning how to draw and predict ionic compounds that have more than one bond in them. So the first thing we're going to do is we're going to use what's called the crisscross method to predict their formulas. So the crisscross method is pretty simple. What you do is you look up the most common oxidation state, which is always the very first one listed on the periodic table. You drop the charges, you reduce the numbers if possible, and then you crisscross them, always writing the positive ion first. So that sounds like a lot, but it's really not. So let's do a few. So the first ones are going to be sodium chloride. So sodium, if you go over here, it is Na with a +1 charge. And now chlorine, this is where you get interesting. Chlorine has lots of oxidation states. We are going to use the most common one, which is the first one. The reason being is that is the one it would have. That's the charge it would have if it satisfied the octet rule. So it's the most common, and therefore, if we're trying to make a prediction, we're going to predict the most likely outcome is probably, most common. So that's why we use it. So for chlorine, it's going to be -1. You can always just write plus and minus, but there we go. Then you crisscross them. So the way that works is I drop the signs. Or ignore them. You can do either one, doesn't make a difference. So you ignore the charges, right? You reduce the numbers if possible. 1 and 1 can't be reduced. And then we crisscross them. So what that means is that the 1 from the chlorine actually tells me how many sodiums I'm going to have, and the 1 from the sodium tells me how many chlorines I'm going to have. So my formula would be written, and I'm only going to do this once, Na1Cl1, which will really be written NaCl because the ones never get included. And then the total number of atoms for that compound is going to be 2. So we're going to count the number of atoms as well. So there's 2 atoms in there. And obviously on something this small, it's not really going to make much of a difference. But as they get bigger, you'll see why I'm doing that. So now to draw the bonding, it's pretty simple. You draw your Na, which has 1 valence electron. Chlorine has 7. You can look them up. Since it's ionic, we use an arrow to show the transfer. And that's it. And the reason I knew that is sodium is 281 and chlorine is 287. Again, you can look that up. And then the Lewis dot's going to look like this. Na is going to be +1. Chlorine will be in brackets. It'll have 8 dots around it. I'll use an X to represent the extra electron. You don't have to, it can be a dot as well. And we're done. Now, this is something that you've already done. So this was like the review, it was the warm-up. We've definitely done this before. The crisscross method might be new, but the actual drawing, this step of drawing the bond, showing the transfer of electrons and drawing the Lewis, you've definitely done. Once we get to the next ones, it won't be the same. So K, if we look it up, +1, oxygen, -2. So again, we ignore the charges, we reduce if possible. 2 and 1 can't be reduced because there's a 1 in it, and then we crisscross it. So the 2 from the O tells me I'm going to need 2 Ks in the formula, and the 1 from the K tells me I'm going to need 1 O. The total number of atoms, 3. The reason I'm having you counting the atoms now is to get used to looking at these and being able to figure out how many of each are there. When we get into balancing chemical equations and things like that, it's going to be very helpful to have a background in this. So I'm really doing this. It may not make sense why I'm having you count them out now, but it's for something that we're going to get to a little bit later in the year where it will become very helpful. Now, how to draw the bonding. I'm going to draw K twice because there were 2 of them. They are 2, 8, 8, 1 if you look them up on the periodic table. And I'll draw 1 oxygen. It has 6 valence electrons. It is 2, 6. And now what I'm going to do is, and I've said this before, the reason you want to follow up the pattern with the Lewis dot diagrams is because when you go around one, you put your first dot here, then your second, then your third, then your fourth, fifth, sixth. And the reason we're doing that is because paired electrons are not going to want to form bonds. Single electrons are. So there's one bond. There's the other bond, meaning this K gives an electron here to make a pair. This K will give up an electron to here to make a pair. And that is the only real difference now is you're going to have more than one arrow. Each arrow represents a bond. When we draw our Lewis dot diagram, watch. I always like doing it this way. This is how I tell students to do it. you start with the formula. Okay, the formula was K2O, so I'm rewriting it. The two Ks, they lost 1 electron each. So they went +1. The common mistake here is to put +2 because they say, well, 2 electrons were lost, well, they should be +2. But individually, they only lost 1. And the fact that there were 2 of them is accounted for in the 2 down here. And then oxygen, well, oxygen did gain 2. So I'll use my X dot system. Bracket the thing, that's a bad bracket, but whatever. Bracket the thing that gained the electrons, -2 charge. Okay, so that is how we do it, and as we do more, you should see it should make a little bit more sense. Let's do the next one. Lithium, +1, nitrogen, -3. Ignore the charges, reduce it if possible, which you cannot. Use the crisscross method. Your formula is going to be Li3N. Total number of atoms, 4. Next, I'm going to draw 3 Li's and 1 N. N has 5 valence electrons. It is 2, 5. Lithiums have 1 valence electron. They are 2, 1. And for nitrogen, again, I do it this way, 1 on each side. And then there's the 5th. So nitrogen's we're going to want to make 3 bonds, 1 here, 1 here, 1 here. 1, 2, 3. Done. And last thing, to do our Lewis dot, we always use the formula. I'm spacing them out a little bit more, so I have a little bit more space. I don't have to do a weird bracket like that. The lithiums lost 1 each, so they went +1. Nitrogen gained 3, it went -3. Put my dots around it. And then I bracket the nitrogen, and notice when I write the formula out, the positive thing, meaning sodium went positive, so it went first. Potassium went positive, it went first in the formula. Lithium went positive, it went first. So I always put the positive ion first. That's just formatting and how it's typically written. All right, next one. Mg +2, oxygen -2. So now here's a trick. We ignore the charges. We reduce if possible. 2 and 2 can be reduced to 1 and 1. And then we crisscross. So now my formula is going to be MgO, and I'm only going to have 2 atoms, not 4. Common mistake I see a lot is people will write Mg2O2 and then get it wrong because that's twice as many. And the reason you don't need 2 Mg for 2O is this is going to be shown here. Mg is 282. It has 2 valence electrons. Based on the octet rule, we know it wants to get rid of both of them. Oxygen is 2,6. It has 6 valence electrons. It needs to gain 2. Well, there's one, there's the other. So it only takes 1 Mg to stabilize 1 O, which is why the formula is MgO, which is why the reducing part of the crisscross method, that's why you can't ignore that, because if you ignored that part, you'd be telling me it takes 2 Mgs to make 2 O's stable. And while it does, when we write chemical formulas, we always write them in the simplest ratio possible. Meaning, like when you make a cooking recipe, you write the recipe to make the basic model. Like, let's say you do your recipe and it uses 1 egg and half a stick of butter and it makes 6 cookies. You don't write recipes where you're like, all right, now take 75 sticks of butter and 150 eggs, and now you're going to make like 8 million cookies. It doesn't work like that. You always write the most simple one you possibly can, and then if you needed to scale up, it's much easier to multiply out. You wouldn't multiply out with these. That's more for chemical equations, which we'll get to later on, but that's the general rule. So don't forget to reduce is the moral of the story. When we write our formula, MgO, Mg lost 2, so it went +2. Oxygen gained 2, it went -2. Brackets around the negative. Next one, this is probably going to be the hardest one that we do. It's definitely going to be the most complicated one, or the hardest to draw. So 2 and 3, we reduce the signs or ignore the charges and then reduce if possible. 2 and 3 cannot be reduced. So the 3 from the nitrogen tells me I'm going to need 2 calcium, and the 2 from the calcium tells me I'm going to need 2 nitrogen. My formula is going to be Ca3N2, 5 atoms. So I'm going to draw it up. My ends are going to have 5 valence electrons because of their configuration. Calcium is 2, 8, 8, 2, and nitrogen is 2, 5. So I know my calciums want to lose 2, my nitrogens want to gain 3. So 1 calcium can give up 2 electrons to a single nitrogen. But that's not enough because the nitrogen wants 1 more. So we can find another calcium to grab 1 from, but then the calcium's stuck because the calcium has 2 that it wants to get rid of. So now the calcium needs to find another nitrogen to give up its next electron to. So now calcium's good, this calcium's okay, but now this nitrogen still needs 2 more, and then at the very end they balance out because then 1 more nitrogen or 1 more calcium is able to do that. So that's what it looks like. 2 electrons go to the first, the 2 electrons from the third go to the other nitrogen, and then the calcium in the middle splits its electrons between the 2 nitrogens. Now, these are super neat because I've drawn these a bunch. I always like putting the calcium on one side and the nitrogen on the other. If you didn't do that, as long as the arrows are going in the same spots, it doesn't really matter how you draw it. Your Lewis dot is going to look like this. Ca3 and 2. CAs went +2 because they did lose 2 each. Remember, this is the individual charge. The nitrogens gained 3 each, so they went -3. And each nitrogen looked like this when it was done. And there we go. Now there is a few we're going to do on the back, so let's flip to the back page. So now with this one, we're going to do 2 more fully, and then these 3 over here, we're just going to worry about their formula. I'll explain why. But let's start with the ones we are going to do. So we've got aluminum and Br. Br is -1. Al is +3. We ignore the charges. We can't reduce. Then we crisscross. So we end up with Al, Br, 3, and we get 4 atoms. When we draw it out, 1 Al, and 3 Brs. The Brs are 2, 8, 18, 7. That's right off the periodic table. The Als are 2, 8, 3. So Al gets 3 dots and it wants to get rid of all 3. The bromines get 7 dots and they want to gain 1 each. So you should see the relationship right away. Aluminum has 3 to lose. The bromines only need to gain 1. So aluminum is going to give 1 to each bromine, and then everybody becomes stable. Final Lewis dot, Al, Br, 3, +3, -1. And there it is. All right, last one. Ca is +2, carbon -4. That's right off the periodic table. Ignore the charges. Reduce if possible. These can be reduced. 4 and 2 can reduce to 1 and 2, or 2 and 1, however you say it. And then you crisscross those numbers, and there's a reason for that, and we'll find out in a second. So my final formula is going to be Ca2C, which is 3 atoms. Now it's gonna, when I draw it out, I'm gonna draw out 2 Cas and 1 C. C is 2, 4. Calcium is, so 2 dots, 4 dots. So as you can see, carbon wants to gain 4 to become stable. That's the octet rule. Calciums need to get rid of 2 each. So it's going to take 2 calciums to make 1 carbon stable, which is why when it's important to reduce, because otherwise you would have predicted that you needed 4 calcium to make 2 carbon stable, and while that will work, that would create 2 separate molecules, and we want the formula for a single molecule or compound, whatever you call it. Last one, Lewis dot, Ca2C, plus 2 each because they lost 2, minus 4, because it did in fact gain 4. Again, I use my X dot setup. They could all be dots, or you could put you could make these X's and these dots. It doesn't matter as long as you're consistent. It doesn't really matter, an X and a dot. As long as you represent an electron, you could use hearts for that. You know, for all I care, it doesn't make a difference. So that is it for the ionic compounds. Now what we're going to look at is polyatomic ions. So the thing about polyatomic ions is they are found on table E in your reference table, which looks like this. It's on page 2. It's called the polyatomic ion chart. And if you look at it, the ions themselves, they have their charges here. They're all listed, so that's easy to look up. And the reason they're called polyatomic ions and they're in a special class is because when you use them, they act as one element. They act as one unit. They are never going to break up or separate. The nice thing is their names are on table E, so if you ever need to name them, which we will eventually be learning, you'll get their names right off table E, and you treat them as if they are one element. So don't treat it as you have element O and element H. Treat it as polyatomic ion OH. Same goes for SO4, and same goes for PO4. So all we're going to do with these are crisscross them. We're not going to draw them, and we're not going to do their Lewis dot because it would be too complicated for us. So we're just going to worry about predicting their formula, and then we're done. So Mg and OH as a group. So OH, if you look on table E, has a oxidation state of -1, and that's not the H, that's the OH as a group, and Mg is +2. So we reduce if possible, crisscross, and my final formula is Mg OH 2. Now if you look at this, I intentionally included a mistake. What I'm trying to say is that I need 2 OH units or groups. What this is telling me is that I have 1 Mg, 1 O, 2 H's. That's not what I want to say. I want to say I have 2 OH's. So for the polyatomics, you're going to have to put parentheses around them if it's more than 1. If this number outside was a 1, then it wouldn't matter. If it were just, I'll do one down here where I don't have to do it. I'll show you an example of that. But for this, you have to have a parentheses, otherwise it's wrong. So for this next one, Mg and SO4. SO4 is -2. Mg +2. Actually, this is a good example. Ignore the charges. Reduce if possible. They can reduce to 1 and 1. And then when you crisscross them, you're just going to need 1 Mg for 1 SO4. So I can just do this. No parentheses needed because I only need 1 SO4 and I have 1 SO4 there. You could put parentheses around the SO4 if you wanted to, and then just left it that way. It's fine, but you'll never see it written that way. It'll always just be written like this, meaning if you don't need parentheses, you typically don't include them, or you almost always don't include them, unless you're trying to visually make something stand out, but that's really it. So MgSO4, there it is. Now the next one, Mg +2, PO4 -3. That -3 is not for the O, it's for the whole thing, just to remember. We can't reduce them. We ignore the charges. We crisscross. So I need 3 Mg's. So I write Mg3, no parentheses around that because that's just an element. And then I need to have 2 PO4s. So I write PO4, close the parentheses, the 2 goes outside. Now, total number of atoms. This is where it gets a little more complicated. You have 2, so for the first one, you have 2 OHs and then 1 Mg. So you have 5 atoms in there because this 2 doubles everything in the parentheses. Here we have 6, that should be pretty easy, 1Mg, 1S4O. And here it gets a lot. We have 13 because you have 3 Mgs, 2 Ps, and 8 oxygen because this 2 doubles that 4 to an 8. So you have 8 oxygen, 2 Ps because there's technically an unwritten 1 in front of the P. So that's why it doubles there. And then the 2 doesn't affect the Mg because it's outside the parentheses. So that's it for this lesson. And the next thing I'll include is some practice problems where you're gonna do a lot of these to get a little bit more comfortable with them.